Hi everyone, my name is Will Stanton and I work at ReturnPath, which is actually right down the road in Brookfield. Today I'm going to be talking to you about deep learning and text mining. So at ReturnPath we have a problem. We process millions of emails a day from tons and tons of different senders, and we want to be able to tag them. But we want to be able to tag them with rich tags in an automated way. Maybe we want to know what kind of products do they sell, what's their industry vertical, who do they sell it to? Are they selling luxury items? Are they selling discount items? Maybe what is their business model? Can we identify, are they a daily deals type site? Do they do flash sales? Something like that. Of course, there's so many senders, we don't want to do this all by hand, and we want to be able to do tons and tons of different rich tags, so we couldn't do it by hand even if we wanted to. I don't want to, by the way. So what to do? So the standard approaches don't work that well for this kind of scenario. So if you do standard text mining kind of stuff, where you create a big document term matrix, count words, count how many words appear of different types in different documents, and try to create a classification model, this is tricky because every classification model needs a training set, possibly a large one. And if you're going to go through and label hundreds of senders with what kind of sender they are, then you might have already solved the problem anyway, right? And that would take forever. A clustering approach is also difficult, and it's problematic because if you have a large clustering algorithm, it only places each item into one cluster. So if we want to have multiple tags, we need to have multiple different clustering algorithms. And each clustering algorithm, if you've ever built one, is kind of hard, right? You have to tune it, you need possibly a lot of data, and it's just kind of annoying. So we thought that we should try deep learning because it's trendy, right? Well, this is what a neural network looks like, right? This is a kind of a toy example of a neural network. You have an input layer and an output layer, and in between you have possibly many hidden layers. And each of these little circles would be called a neuron, and you'd pass tons of training data through this network and adjust parameters to make this network make the predictions or groupings that you want it to. So now what's deep learning? Well, deep learning is essentially just doing neural networks with a ton of hidden layers. So in the example I showed, there were only 2 hidden layers, and way back in the day, a few years ago, everybody would only use a couple of hidden layers at most, maybe a few, partly because it's very hard to train effective neural network models with more of them, with more layers, and also because people didn't used to think you could get a lot more benefit, from extra layers. But in the last few years, there have been some great papers and a lot of great technology that's come out that's shown that deep learning can be really, really good for kind of deep cognitive type tasks like text classification, image recognition, speech recognition. So we thought maybe it'd be good for this kind of rich kind of tagging we want to do using our email data. So a key concept in neural networks, and especially deep neural networks, is the concept of a distributed representation. So you can imagine in your brain when you look at, say, Mike, then you don't just see a collection of pixels that are projected onto your retina, right? Instead, these pixels are combined from just pixels into collections of edges, and there's research to support this, then into different shapes, typical shapes like a nose or an eye or a mouth, and then into typical facial types. So when I look at Mike, I don't just see Mike as an image, I see an entire structure and collection, a huge network of neurons are all firing at different levels, at different times, and that's what the representation for Mike's face is. So that's a distributed representation. You can imagine doing the same thing with text. So some recent papers have shown that you can do the same kind of thing. Letters go to words, phrases, and even up to concepts. This is where I would normally say any questions, but can't do that. So now, what's the difficulty with deep learning? So we want to apply deep learning at ReturnPath, right? But there are some real challenges. So the biggest challenge is that it's very difficult to actually train a neural network, a deep learning neural network, and there are a lot of real technical reasons, but you can just imagine that each of those neurons has associated parameters. So the more layers you have, the more parameters you have. So very quickly, by adding lots of hidden layers, you end up with a very, very complex model with hundreds, thousands, maybe even tens of thousands, hundreds of thousands, or millions of different parameters. So, and each different feature that you add, each different variable also means new parameters. So with extra hidden layers, you get an exponential growth in the difficulty of training the model. Now, real human-generated text, like we have a return path, with things like email subject lines or email content, is essentially infinite in dimension, right? There are as many features as you could imagine, and it's also essentially infinite in size. You could imagine that you would want to run through some sort of model with every email that we've ever collected, which is a lot. So the solution is use Word2Vec. Word2Vec is a very new algorithm. It was developed by scientists at Google in 2013. And there was a Python implementation created in 2014, which is good for me because the other one was in C, you know. Actually, and amazingly, the Python implementation is actually faster now. It learns distributed vector representations of words. So that's why it's called Word2Vec, and it uses neural nets. Now, technically, it's not deep learning, so any experts out there, don't get mad at me, right? Because this is actually a matter of some controversy on the internet. But it does learn distributed kind of deep style representations just very efficiently using less big neural nets. So what's the output of Word2Vec? So you run a bunch of data through Word2Vec, and what do you get? You get each word encoded as a vector of floats. So for example, you might have a vector for the word queen and a vector for the word woman. The length of the vectors is the dimension of the word representation, right? So the key concept of Word2Vec is that similar words have similar vectors. So this gives you a way of comparing words by simply doing vector operations like cosine similarity. So what's the great thing about Word2Vec as opposed to regular deep learning on text or some other model we might use? Well, first of all, it's incredibly scalable. At Google, they've trained it on hundreds of billions of words, and they think they could go up to 1 trillion. It uncovers really cool, deep, latent structure of words. Now, this is something that Word2Vec does really well and it's very interesting and cool. So it can solve analogies, like king is to man as queen is to woman, or Paris is to France as Berlin is to Germany. I almost forgot what capital Germany is. So it can solve one of these things is not like the other problems, right? These things that are very, very easy for humans, but really difficult for machines. And it can be used for really interesting, true natural language processing tasks like machine translation or sentence completion. So how does it work? What do you actually do? Well, it's very simple. You just feed the algorithm lots and lots of sentences. This is a totally unsupervised algorithm. You don't have to do any tagging, any part-of-speech tagging, lemmatization, any of these things that take a lot of work for real natural language processing. You just feed it lots of data. So what does it do? It trains a neural net that encodes the context of words using something called a skipgram architecture. So it's basically trying to predict what's the next word, what's 2 words from now, what's the previous word, what's 2 words previous, and so on. So it's trying to learn the context that words appear. So we did this at Return Path to solve our problem. So we implemented it in our consumer data stream, which is basically just millions and millions and millions of emails. We passed 30 million unique email subject lines, which was about 300 million words, and concatenated sending domains. We trained it using this Python implementation of Word2Vec, and we got some very interesting results. So there's no magic here. I haven't filtered anything. This is actually real Python code that I ran. It's very simple. And I put in groupon.com, and I said, well, tell me similar domains that have a similar context. And it spits out dozens and dozens of similar deal sites, like Living Social, for example, or WagJag, or Woot.com also appears. Finding apparel sites like Gap, right? It spits out all kinds of similar sites. Now remember, this is totally unsupervised. I haven't labeled any sites or any apparel sites, right? So that's the real cool and interesting stuff about this. Some other things, we can encode, Word2Vec encodes context and relationships between products, like iPhone is to Apple as Galaxy is to Samsung. Or distinguishing between different companies, like a group of 3 hotels and Walmart. It knows Walmart is not a hotel, and it detects that automatically, even though I never told it what a hotel was. Other possibilities, we think we could find, perhaps construct automatically high-performing subject lines, using the sentence completion capabilities, for example. So that would be a real holy grail kind of interesting thing for email optimization. You can try it yourself. There's a C implementation, but I recommend the Python. It's a little simpler and it actually runs faster, and Python is more common for data science anyway. It's very easy to find, and you can just go to the Gensim site. You can also get pre-trained models to use if you don't want to train it yourself and just want to test it out. So thank you so much for listening. Thanks to Data Science Association and Michael for organizing this. You can find the slides on my website, willstanton.com, and also Return Path is hiring, so we're an awesome place to work. We do this kind of cool stuff all the time. So please email me or come talk to me if you're interested. So thank you very much.